In this lecture video, we're going to talk about measures of relative standing, including z-scores and percentiles. Z-score is the number of standard deviations that a given data value is above or below the mean. It's a way that we can level the playing field and take different values, even from different populations, and be able to compare them on the same scale. Here's how a z-score is calculated. For a given data value x, z is equal to x minus the mean, which is x bar for working with a sample, divided by the standard deviation, or s, when we're working with a sample. If we're working with a population, we could rewrite this as z equals x minus mu divided by sigma. It's still the difference between that data value and the mean divided by the standard deviation. When we're calculating z-scores, we always round to 2 decimal places, no matter what. This way, we can use standard tables of z-scores, and again, we're taking data values from any set and translating them to the same scale. Z-scores are expressed as numbers with no unit of measure. A data value is considered significantly low if its z-score is less than or equal to -2. Or it's considered significantly high if its z-score is greater than or equal to +2. If an individual data value is less than the mean, then its corresponding z-score will necessarily be a negative number. That's because the difference between the data value and the mean will be negative. Here's a sketch of a normal distribution. Suppose that we have a data value x here. That x value would have a z-score that is a positive number because it's greater than the mean, and that z-score would be between 0 and 1 because while it is above the mean, it's not a full standard deviation above the mean. Suppose instead our data value was here. This data value would also have a positive z-score because it's above the mean, but this time the z-score is between 1 and 2 because it's more than 1 standard deviation above the mean, but not 2 standard deviations above the mean. If our data value was instead here, it would be negative because it's below the mean. Remember, the numerator for calculating z-score is x minus mu, and if x is smaller than mu, then that numerator is a negative number. Here we have a z-score that is between -2 and -3. It's more than 2 standard deviations below the mean, but not a full 3 standard deviations below the mean. We consider data values that are more than 2 standard deviations above or below the mean to be unusual. More than 2 standard deviations above the mean, we consider unusually high. And more than 2 standard deviations below the mean, we consider unusually low. And data values in between, we consider usual. Consider that these dividing lines between usual and unusual correspond to z-scores of -2 and +2. That is, data values that correspond to z-scores less than -2 are unusually low, and scores that are greater than +2 are unusually high. Let's take a look at this example where we will have a chance to calculate some z-scores and interpret their meaning. Julie's test score on her last chemistry exam was 72%. The class average was 78% with a standard deviation of 8%. First, we'll find the z-score for her chemistry test. Since the population in this case is the entire class, and the class average was calculated using the entire class, we'll use our notation for a population. So, we can calculate z by finding x minus the mean divided by sigma. In this case, our data value x is Julie's test score, 0.72. The mean for the class is 78%, or 0.78. And the standard deviation, sigma, is 8%, or 0.08. So we find that the z-score in this case is equal to 0.72 minus 0.78 divided by 0.08. Julie's z-score is -0.75. It's negative because Julie's test score was below the average, but it's only 6% below the mean, not a full 8%, not a full standard deviation below the mean. On her math test, Julie got a 76%. The class average in that case was 79% with a standard deviation of 9%. On which exam, chemistry or math, did she have a better score relative to the rest of the class? These two data values, her chemistry exam and her math test, are from two different populations. And so we cannot simply compare the 72% and the 76%. What we can do is calculate the z-score for the math test and then compare that to the z-score for her chemistry test. In this case, the data value is her score, 76%, or 0.76. The mean, mu, is equal to 79%, or 0.79. And the standard deviation, sigma, is equal to 9%, or 0.09. The corresponding z-score for Julie's math test is equal to x, 0.76, minus mu, 0.79, divided by sigma, 0.09. That means that the z-score is negative 0.33. This z-score is also negative because her test score was below the class average. But it's only 3% below, not a full 9% below. It's not a full standard deviation below the mean. In fact, it's only a third of a standard deviation below the mean. So now we can compare these two z-scores. Relative to the rest of her class, Julie performed better on her math test. She's closer to the mean. The z-score of negative 0.75 is lower than the z-score of negative 0.33. Putting these two scores on the same scale, we can clearly see that her math test was better than her chemistry test. Now we have the question, was either score unusual? Remember our definition for usual and unusual. Usual data values are no more than 2 standard deviations away from the mean, and unusual data values are more than 2 standard deviations above or below the mean. In both of these cases, Julie is not even a full standard deviation away from the mean, so neither of these test scores are unusual. Another measure of relative standing is percentiles. Percentiles are measures of location. We call them P1, P2, all the way to P99, which divide a set of data into 100 groups with about 1% of the data values in each group. For example, the 50th percentile, which we denote P50, has about 50% of the data values below it and about 50% of the data values above it. In fact, the 50th percentile is right in the center of the data and is the same as the median. The 25th percentile, denoted P25, has about 25% of the data values below it and about 75% of the data values above it. Suppose a child has a height of 3 feet and they are told that they are in the 25th percentile. That would mean that approximately 25% of all children that same age have a height that is less than this child. And about 75% of all children the same age have a height that is greater than this child. That's what it means to be in the 25th percentile. To calculate the percentile for a specific value, we need to take the number of values that are less than that data value x and divide it by the total number of data values. Then we multiply by 100. The final step is to round to the nearest whole number. For example, if we look at this data set containing the values 5, 4, 6, 7, 3, 9, and 2, we can find the percentile for the data value of 4 by finding the number of values that are less than 4 and dividing it by the total number of data values. Let's first sort this data set from least to greatest so we can more easily identify the data values that are less than and greater than 4. The data value that we're interested in is located here, and we can see that there are 2 data values less than 4, and the total number of data values is 7. So the percentile for 4 can be calculated by finding 2 over 7 times 100. This gives us 28.57, and rounded to the nearest whole number, we find that 4 is in the 29th percentile. Suppose we want to do this process the other way around. Rather than finding the percentile for a certain data value, we want to figure out which data value a certain percentile corresponds to. In order to do that, we need to be able to calculate what we call a locator value, and we denote that with a capital L. In this equation, K denotes the percentile being used, and N is the number of data values in the dataset. Here's the process. The first thing we need to do is sort the data. We want to arrange the data in order from least to greatest. Second, we will find L using the equation above. The third step depends on if L is a whole number or not. If L is a whole number, then the value of the kth percentile is midway between the Lth value and the next value in the sorted set of data. And we can find pk by adding the Lth value and the next value and dividing by 2. If L is not a whole number, then we simply round L up to the next larger whole number, and the value of pk is this Lth value, counting up from the lowest data value. Let's try out this process with a couple of examples. First, we're going to find the 40th percentile in this data set. Notice that our data set is already listed from least to greatest, so we can go on to step 2 and calculate L. To calculate L, we need to compute K over 100 times N. In this case, our K is 40 because we're interested in the 40th percentile. And our N is 6 because there are 6 data values in this set. So L is equal to 40 over 100 times 6, or 2.4. Since L is not a whole number, we find our Lth value by rounding 2.4 up to the next whole number. That is, we are interested in the third data value. Now we know that the third data value is the 40th percentile. So counting from the lowest data value, we find that the 40th percentile is 17. That is, P40 is equal to 17. In this next example, we're going to find the 25th percentile. Our data values are 5, 6, 10, and 13. So our K value is 25, and with 4 data values, our N is equal to 4. So when we calculate our L, we have 25 over 100 times 4, or that L is equal to 1. Since this time we have a whole number for our value of L, the percentile that we are interested in is between the first and second data values. Starting from the lowest, the first data value is the 5 and the second data value is the 6. So we can calculate the 25th percentile by adding these two numbers together and dividing by 2. 5 plus 6 divided by 2 gives us 5.5. So 5.5 is the 25th percentile. Hopefully you can see the difference with what we do when our locator value is a whole number or not. That concludes this lecture video on measures of relative standing.